evening, everyone. I'll be discussing the impact of autonomous vehicles on transportation system performance in Texas Triangle. I am Mansha Swami. I'm a postdoctoral research associate at the Center of Transportation Equity Decisions in Dollars, CTED at the University of Texas at Arlington. I'm fortunate to have the lead authors of this research with us today, Professor Pan and Professor Mumsik-Shun. And then let me start with the presentation. So this is the outline of my presentation. As we all know that megaregions are a very dynamic and evolving concept within the urban planning arena. And the more we see the development of megaregions as economic powerhouses, we see that they are interconnected entities wherein there is an interaction between cities, industries, and communities. And these interactions are extending beyond the traditional boundaries of geographical areas. And when we see these intertwined, complex interactions happening between these communities, people, exchange of goods, and so this has a very significant impact on the economic situations of that particular megaregion. Also, the megaregions are going to be mostly housing a lot of economic activity in their encompassment. Also, in Texas Triangle, which is the case study that we'll be studying, we have Texas Triangle megaregion, which comprises of Dallas-Fort Worth, Houston, San Antonio, Austin, and as you can see, there's going to be 70% of the population of Texas is going to be concentrated in this Texas Triangle megaregion. So from that point of view, understanding a particular phenomena of transportation system within a metropolitan area or within a megaregion area is a completely different concept. So we decided to study the impacts of autonomous vehicles and their adoption on the transportation system with our case study as Texas Triangle. So and we all know about autonomous vehicles or self-driving vehicles, and we are all aware about the fact that we are transitioning from, some cities are transitioning from level 4 to level 5 of automation, and some cities are trying to reach level 6, and there are companies like Toyota, Waymo, who are trying to do their testing in order to make sure we are, safe to say that we have reached full autonomous levels and operations. So once these autonomy of autonomous vehicles increases, and once they are completely without human intervention, even now we see a lot of changes that occur in the backdrop of where autonomous vehicles are in the transportation system. Many of these changes are just like cost efficiency, there is optimization of space and dimension, there is more additional accessibility, there is increased roadway capacity and reduced traffic congestions, and we have urban planning that needs to be reimagined because of all these changes happening in the transportation systems. So out of all these parameters that the autonomous vehicles are going to alter in the urban scape, I'm going to focus more on the roadway dimension, capacity change, and the traffic congestion, because these are the scenarios that we have taken in our research and tried to understand how the transportation system responds to these two scenarios. So we know that the megaregions are influenced by all these complex urban interactions that happen between different metropolises. And for now, if we can say that all the kind of data and analysis we do based on the metropolitan NPO data, that is not sufficient to understand the complex environment of megaregions. So we extend our methodology to understand how the megaregions are behaving in response to transportation system. And for that, we would need integrated urban models to understand that. So previously, Professor Pan has also studied a truck flow model in the megaregion context, which was published as a study in the Texas Triangle megaregion itself. So this is an extension of that study, but the new parameter here is that they have incorporated AVs into the traffic stream. So the objectives of my research, or the prime focus areas, are going to be to focus on the movement of AVs in the megaregion context, and also the impact of these AVs in the traffic scenarios that we have tried to build up in the Megaregion context. So there are different scenarios that we have taken. Two of the scenarios are based on capacity increase. Since AVs will be incorporated in the traffic streams, we are expecting more optimized use of road space, and there's going to be a subsequent capacity increase. So we increase the capacity by 50% and by 100% to see how the system responds to that kind of a change. And for traffic growth, we have projected a 1% lower bound and a 3% upper bound change. So these are the 4 different scenarios that we're going to study as a part of this research. So this research has the scope which is limited to GIS-based Megaregion transportation planning model, which has been used here and is mainly focusing on 2 layers, geographical layers. One is about the intra-regional transportation, and one is about the inter-regional transportation. We have also considered both passenger and freight flows in the inter-regional as well as the intra-regional in these 2 geographical layers and the modeling, so we can study the whole system and in a more holistic manner. So the improvement of system performance and the traffic growth leading to changes in the travel demand, and these 2 for both the personal and the freight transportation. So our data and methodology has taken some inspiration from the Southern California planning model, which has already taken up 3 iterations over the years and evolved itself into incorporating more parameters and a better transportation demand modeling. So as the interregional and interregional data processing framework has already been processed by Professor Pan in 2006 and Giuliano in 2010, we extend this study to AV incorporation. As you can see in this analytical framework, over here we have 3 types of data-based inputs. One is the intra-metropolitan transportation data processing, including the passenger trips and the truck trips, and then is the inter-metropolitan data processing, again including the passenger trip data and the freight trip data. But our units were not consistent, because when we were trying to study the freight analysis framework and the commodity flows from the CFS survey of 2017 and the US Bureau of Statistics data, international trade data, the data was available in the form of value and tonnage and ton miles and commodities and modes. So we needed a transportation data tool function to make sure that these varied units are converted to PCE values, so our analysis becomes simpler. And then we are processing this entire data in the 3rd process, which is Megaregion transportation data integration on GIS platform, which I have told before has 2 geographical layers for inter and the intra-regional. And then further we go for Megaregion network modeling, which helps us to study these scenarios, as I mentioned before, on capacity and traffic growth. And these scenarios can further tell us how the system performance is altered by the scenario and the AV inclusion. So we know that we have MPO data available with us for all intra-regional trips, but for inter-regional trips, we have taken data from Commodity Flow Survey, from the US Census Bureau International Trade Data, and then we have developed the Freight Analysis Framework, which is the FAF, which takes care of all the paths and flows of our freight-based movements within the transportation system. Also, we have tried to take data from American Community Survey for different county level interactions between commuters' workspace and their residence location. So the unit of analysis is TAZ, and this Texas triangle, as you can see, is our entire Megaregion analysis zone, incorporating Dallas-Fort Worth, Austin, San Antonio, and Houston. So this is the model, and we are trying to minimize the costs over here by understanding the path and the flow on the path, incorporating the freight as well as the personal vehicle movement together. As you can see, our internal and external zones that we have considered for this study, we have considered several external zones and several internal zones. Internal zones are very clearly being taken from the MPOs, and external zones for understanding the behavior for intermetropolitan transportation flows. And the traffic volume trends for projected for the future years were for 1 and 3% in the lower bound and in the upper bound scenario. So this is just one map showing the results of the personal vehicle travel time in minutes. In order to make sure you were able to see the difference very clearly, I've split it into two for northern and the southern region of the Texas. As you can see in the northern region of the Texas, which is primarily areas surrounding Dallas-Fort Worth metropolis, if you see the private personal vehicle travel time in minutes, we see a significant reduction in the personal travel time, vehicle travel time. You can see the maximum time over here is reduced from 146 minutes to 113 minutes, apart from the other time intervals also. So there is a significant reduction of around 45% in personal vehicle travel time when scenario of base is compared against the scenario in which we increased 100% capacity. Further, the same analysis map is there for the southern Texas. So this is just to make sure you understand what's happening in the entire Texas. And if I show you the fleet vehicle travel time in northern Texas, you can see again there's a significant reduction of about 12%, which is good for the base scenario as compared to the scenario in where there's 100% increase in capacity for the fleet vehicle travel time. Further, when we look at this is the southern part for the fleet vehicle travel time, and as a consequence of reduction in travel times and increase in miles traveled, we see that personal vehicle accessibility has also increased many folds for base scenario and the scenario where there is 1% growth in traffic corresponding to 50% capacity increase, which is this lower scenario. And then further, the third scenario, whereas there is 3% upper bound growth in traffic and 100% capacity increase. So you can see across these three scenarios how accessibility of personal vehicle has changed. And then this is for the southern Texas. This is the results that I want to share with you. As you can see, there is a significant increase in accessibility, and we see a reduction in fleet vehicle travel time in the case where capacity is increased. Further, a reduction in private vehicle travel time when the capacity is increased. A significant similar increase in miles traveled for both private and fleet vehicles, and private vehicle volumes and fleet vehicle volumes have also increased in the traffic growth scenarios. So the main conclusions of this study are improved accessibility, reduced travel times, improved accessibility by 85 to 87% for private and fleet vehicles, and reduced travel times by 46 to 24% for personal and fleet vehicles, increased distance traveled by approximately 80% for both personal and fleet vehicles, and traffic volume growth by approximately 81% for both personal and fleet vehicles, which can be a very significant source of insight for policymakers who want to plan the urban areas in order to incorporate AVs in the future transportation systems. So that's all from my side. Thank you. If you have any questions.